Okay, so I guess we'll go ahead and get started with our last lecture of the semester. Um, because of the online platform, because this was a summer course, we didn't get to cover every topic that I would want, but we did cover the major things that I think as data scientists you need to know. Gradient descent, what the gradient is, multivariable functions, vectors, matrices, the column space, and invertibility. With all of that information, you're already capable of formulating interesting data-centered models. For example, recall early on in the semester when we were learning about linearity, we modeled the price of housing. We had this housing data set, and we used this linear regression algorithm from sklearn, and we modeled that data with that black box information, that black box of a linear regressor. But we didn't know how to do it ourselves. We just called on a function that was pre-built into the package, right? Well, today we're going to do it. We're going to learn how to perform linear regression from scratch. And there's two different ways to do this. There is a linear algebraic way, and there's a way using gradient descent. They're both equally useful. Just in some instances, it's preferable to have one way over the other. And I'll get to that when we start talking about it. So let's recall what linear regression is. So okay. So linear regression deals with labeled data. So we have labeled data. Okay, I'll call it script D. So this data consists of feature vectors and numerical labels. Okay. And if we plot this data in 2 dimensions, it will have something like this. So we have y, x. So y is going to be the numerical label for a given feature x. So okay. And the data can look maybe like, I need to make a better chart maybe. No, I can do this. So maybe like 2.5, or up here at like 3. 3, we're down here at like 1.5. 3, we're also up here at 3. And then 2 at 3, and then 3 maybe at, now maybe I want something else, like maybe like 1 up to 3, and then 3 goes up to maybe 4, like that. And for the purposes of doing this all by hand, let's just leave the data as that, okay? And we want to fit a line to this data that will be our prediction model, right? So we want a line like that, called y hat, which is equal to a slope, which we'll denote by w, times your input feature x, plus some bias or intercept. Okay. Now, for each of these values, we want our line to equal the desired output. Okay? We have to somehow figure out a technique for finding this line. That's the whole goal. So we can write this as a system of equations, actually, right? Because we have 1, 2, 3, 4, 5. So we have 5 data points, feature vectors with labels. So we can have something like x1. So we want our weight times x1 plus our bias. We want that to equal the label for that data set, that feature, right? Like if we put in a 1, so like if that's like our first data point, it's like what, 1, 3. So it'd be like a 1 and a 3 right there. Okay. And then we also want our line to equal, it'd be desirable if our line, our given slope and intercept also produce y2. Okay. So like this is like 1.42 or something. 1.492. So for a given weight and bias, we also would like that to be true. So that'd be 1.4 and that'd be a 2. But then we also want that to hold for the third data point. What is it, like 2, 1.5. And then we also have 2, 3. And we also have 3, 4. So there's 5 total data points, labeled data. So we have this system of equations that we would like to solve. Does this remind you of some of the matrix algebra that we've been doing lately? Because it should, because we can write this as this matrix vector product. Three, 4, 5. Right? W times this column plus B times this column is equal to that. These are equivalent statements. Now, obviously, this matrix is not going to be invertible. Okay? There's not going to be a solution to this. Like, no line is going to hit all of those points. So there is no solution to this. And it's a big, tall, skinny thing. It needs to be square if there's any hope for us to invert it to find the solution. But we can change the equation. So let's actually call this matrix, let's call it X. And we'll call this W. And instead of B, I'll use weight 1, weight 2. So A1, A2. A1, A2. So, and we'll call this vector y. So what we can do is we can make a new system by multiplying both sides of this equation by x transpose. X transpose, now why would I do that? Well, suppose x is m by n. The transpose of x is what? N by m. What's the dimensions of the resulting product?
N by n.
Right. In fact, we could even like see that, like, yeah, it's just n by n, which will be squared. And then there's a hope. So if we multiply both sides of this by x transpose, we get and we'll call a solution to this new system W tilde or something, W prime, W tilde, doesn't it? So what we're doing is we're trying to modify the equation to get now an approximate W, right? This W is not going to be the same W that would be an exact solution to this system, but there's a hope that this is, so this is square at least. There's a hope that this is invertible, which means if this is invertible, we can solve for W tilde, which will give us an approximate solution to our problem here. Okay, and in practice, x times x transpose is going to be invertible. And you'll learn about the details of that when you take advanced linear algebra and optimization. For now, just know that in practice, that matrix is invertible. So let's walk through the steps. We have x times w is equal to y, and then we multiply by x transpose on both sides. And then we invert the matrix, multiply both sides by that. Matrix times its inverse is just the identity. Identity times W. Oh, this is our W tilde now. And then here we have, oh, this is inverse, by the way. Make sure that's there. There. So these are what are known as the normal equations. Equations because this is a system of equations. It's a single matrix of equations, but there's many equations built into this. Right, for W1 and W2, they're going to have values in there. So these are called the normal equations. Okay. So let's go ahead and figure out what W tilde is. I think I have a Jupyter notebook open right now. I have a small little baby data set. Let's see what this is. And again, you could do this by hand. In this small case, you could, in fact, I encourage you to actually multiply like with those numerical values, right? So let's be clear now what goes in here. So 1.4, 2, 2, 3. That's all the features. And then the labels for those corresponding features are 3, 2, 1.5, 3, and 4. I don't want to take the time to do it right now. I think it misses the point to do that. But I do encourage you to multiply the transpose of that matrix times itself on both sides of this, and then compute the inverse using Gauss-Jordan elimination and work it out by hand. At least once in your life, do that. But we're not going to do that. So let me go ahead and share my screen. Okay. Get rid of all this stuff. I think I have a Jupyter notebook open somewhere already. Yeah, let me just get rid of all this. Let's go ahead and restart kernel. Okay, so we're gonna need pi as in p, and then we're also gonna need matplotlib. Okay. All right, so now we need our data. So I'll say d features equals np.array 1, 1.4, 2, 2, 3, and the labels equals np.array. What are they? 3, 2, 1.5, 3, and 4. Okay, so if we wanted to just take a quick look at the data, there goes the data. Okay. I like to change my markers up. Okay. And maybe I'll change the color too. Okay, so let's go ahead and make our vector x. And the way that we can do this is with, let me see. Actually, I haven't done this in a while. Let me check something real fast. I'm just making a, yep. Let me do this. I wonder, this is what I was looking for. 2 by 2. Okay, yeah, that's how you make a matrix. All right. So we need to make our matrix X, which corresponds to, I wonder, I want to play with this real fast and see something. I'm just trying to do it efficiently right now. Yep. Two by 5. That is not what I want. I need it to be 5 by 2. So maybe I can okay. So this isn't the matrix X. I was just playing around with it. What we really need is our features, and then we need a bunch of ones for the bias. So I can just do np dot ones, and how many we need? 1, 2, 3, 4, 5. 5. That transpose it. There's our matrix X. And if I check the shape, oh, maybe I needed there. 5 by 2. If I look at X now, there. Okay, so again, it might seem off that like I'm slow with these NumPy commands. It's just typically I use another programming language called Julia when I do my own personal linear algebra stuff. So I always forget the methods to the NP module. Okay, so what do we want? We need to solve the normal equations, which means we need to look at oh, we need our y too. So y equals np dot, oh no, we already have it. D labels. Okay, so if you look at the board behind me, you see X transpose X inverse times X times Y. So real quick, let me look up inverse. Oh, this is kind of convenient, but I want the fast way. 1 second. I guess. God, I wish I could show you this in Julia. It's just so much easier. Or prettier, I would say. All right. So going back, so that's the command. So I want to look at the inverse of X dot transpose times X. And then multiply that times X dot transpose. Yep. And then multiply that times Y. And this will be my W tilde. Oh, NP dot linear algebra. So there's my W tilde. That solved that system behind me. Okay, so now we have my weight, my slope, and my intercept. So if I come back up here and then make this, and then I can plot a line, PLT dot plot. I need to make a domain real fast. Maybe start at 0.5 and go to 3, maybe. 5, 3 with increments of 0.25. And we can plot domain and then x times w tilde I'll just write it out. Not worry about that. So 0.62062937 plus 1.53321,678 for x in domain. So let's see what happened. There. I can make the line a little bit better by increasing this. There. There is the regressor. That's the regression line for our data. And all we did was solve the normal equations. The inverse of x transpose times x transpose times y. Solving that gives us our weights. Okay. So this, again, with regression, you have to be careful because the data that you use is very important. So we're not talking about training data, testing data right now. All I'm trying to do is to show you how to build a line for a given data set. Okay. So that's how you solve this problem of finding the line using linear algebra. Okay. And it's all about matrix products, inverses, knowing that a matrix is invertible, understanding how to set up the equations in terms of linear algebra. Okay. But there's another way. This works. But when you have a huge system, like this is a tiny system of equations, there's 5 equations. But when you have a huge system of equations, you are inverting a large, or if you have a large number of variables, right, you are inverting a huge matrix. Matrix inversion is not an easy thing to do numerically if you have a huge matrix. So is there another way to build this? Yes, and that's gradient descent. And I know that we've talked about gradient descent before. I just want to show you how to put it into practice and relate it to linear algebra. This course is about linear algebra and multivariable calculus. We solved this problem using linear algebra, and now we're going to solve it using multivariable calculus. We need a cost function. And the cost function that we're going to use for a given weight vector W is 1 over 2n, where n is the number of feature vectors times the sum I is equal 1 to n of what's the best way to do this? The norm of W transpose times xi modified minus yi all squared. So xi is simply x hat I is the block vector x1. So for the ith feature, the ith feature vector, x hat is the vector obtained by adding the 1 there, and that 1 there is because w, so w still has the form w1, w2. So then w1, so when you take the inner product of w and x hat, you get w1 times the feature plus w2 times 1. So that's like your bias again. And you want that to equal the actual numerical value for the output. Okay. But now that we have this cost vector, we can optimize this using gradient descent. So what does this really look like? Another way of looking at this, I suppose. Or like that. So then if we look at the partial derivatives with respect to W1, we take the derivative of the outside, the 2 hits that 1/2, so we're going to have a 1 over n on the outside. And we do that for each of the pieces. The derivative of the outside made the 2 come down. And then the derivative of the inside is just the coefficient of W1, which is xi. If you wrote it all out, you would see that this is the partial derivative of that function with respect to W1. What's the derivative of the outside? 2 comes in front, times the derivative of the inside is just xi, the coefficient of W. You do that for each of the pieces, each of those 2's will come out and you don't have the 1/2. If you do it with respect to W2, it's the same thing, except for now, derivative of the outside, the 2 comes down, gets rid of the 2 over here. And now there's no coefficient of W2, it's just 1, so there's nothing multiplying it out here. So then you take a guess at W like that. And then once you do that, you can then update your full with the full gradient. So then W, I hate to emphasize it's a vector, I'm going to put that. So then W k plus 1 is equal WK minus alpha times the gradient of C at WK. Okay? Which means that W1, W2 is going to be equal to, or go to, W1, W2 minus alpha times that. like that. Yeah. Trying to see if there's a really simple way to write this with vectors instead. Oh yeah, I could make a vector of all of these entries and then just multiply that times all of the x's, make a vector which is the same as this vector, multiply times the ones vector. Okay, and you iterate this until your error is low enough. Your error or your cost is low enough. So iterate until this is small. So let's look at what that would be if we program it. Okay, so what is our data? Where is it? So D features. Okay, D. Okay, so I have all my x's, I have all my y's. So now I need some random weights. I need 2 of them. Yep. Okay. So those are our random weights. And we need to pick an alpha. I don't know, 0.001. Two maybe is a guess. And then we have the full gradient. We know the partial derivative, so we can just do this. So let's say, let's make a function to return the gradient. Gradient of C with respect to W. X and Y. So so D W1 is going to be, I need to know what n is. N is equal to the length of my feature vector. Okay, so dw1 is going to be the sum of w0 times xi plus w1 minus yi, where I in range maybe length of, n. And then divide that by n. Oh, almost forgot. I need to multiply this by something, right? I need to multiply this by the xi. Yeah, and then times. And now this is basically the same for the second derivative. 2. But now we don't multiply by this. So then return np dot array dw1 dw2. Okay. Oh, I should probably write my cost function as well. So maybe I'll just do that above this one. Cost for a given W and my X's and Y's. It's almost the same as this, right? So let me just grab this guy. I'm going to return. So now instead of dividing by n, we're going to divide by 2n. We're not going to multiply by that. We're going to raise to the power of 2. So that should be the cost for a given W. So what is the cost right now for our W, D features, D labels? Oh, I need to define n. That's our cost right now. Okay, so let's go ahead and do this. So we're going to iterate this a bunch of times. So for underscore in range, I don't know. Let's do it like 25 times maybe. And I want to save my costs, by the way. So I'm going to do an error vector like this. Okay. So let's do count to count. For I in range 25, W equals W minus alpha times grad C W X Y. This is not the most efficient way to do this. I'm just showing you the concepts right now. So please remember that. And then, so let me just like populate these things here. Count and then error dot append. Okay, and now this needs to change to this business here. All right. Maybe just to be safe, we'll do it like 50 times. Oh, it already ran. So now let's look at PLT dot plot count error. Look at so the error, right, is really high at first, but then you see that the cost function, okay, that's all we're doing here is we're appending into the cost function. So maybe like X label, now I'll just leave it like this for now. So this is the cost function is decreasing as we increase, as we get closer to 50, right? Maybe what I can do, let's just try this again. So I'm gonna try with a different W. W equals NP dot append, or not NP, what am I doing? NP dot random dot rand normal distribution 2. And then let's do this like maybe 100 times. So you see that the cost spiked up, but still overall the trends were that the cost was decreasing. What is the last cost? 7. Let's see how well our line looks now. So back here, but now instead of that, we'll have W0 plus W1. There's our line there. So here we use gradient descent to find the line, right? And maybe what I can do to illustrate what's happening here is say, okay, weights equals nothing, and then weights W, and then here I'm gonna do weights dot append W, so I can keep track of those things. Whoa, that one learned it really fast. Yeah, let's do another one. Sometimes that'll happen. There, that looks better. So let's look at another line here. So let's look at what's happening here. So I'm gonna say weights now. Let's look at like the second one after we iterated it 2 times. Weights 2. And then weights maybe like 17 or something. And then finally, we'll look at it when we're at the end. We'll do color equals green. Color equals orange. And then finally, color equals red. So see how we are way down here at first, and then after 17 updates of gradient descent, we've changed our weights to fit here. And then eventually we've come up to the last iteration, which is this line here, which looks very similar to the solution of the normal equations by matrix inversion. Okay. So this, I think, is a good place to stop today's lecture.
Sorry, could you show us the final weights so we can see how similar they are to the
Yeah.
weights?
Yeah. All right, so W there, and then the weights up here were this guy. So let's go back down here. There's that.
Okay.
So it's not exactly the same. But like, let me like push it a little bit. And maybe say alpha equals 0.0012. Okay, so now the red line is the final line. Still different. But they're just different ways to find a line approximating that data. And this data is actually like really bad in a sense because there's only 5 points. And it's not going to be, gradient descent probably would work better with more points. In fact, that's when you would choose gradient descent over solving the normal equations. When you have a ton of data, you would rather use gradient descent than invert a huge matrix. Okay. All right, so that'll be it for today's recording. I'm gonna go ahead and stop it there.